Okay, today I was going to talk through this script called simulationscript.r. We'll start survival analysis next week. So in this script, I just have a variety of short simulations to illustrate a few statistical concepts. One of them that I'm going to do, I'll do it first, is what came up last time, which is how, like, model selection. How do we do model selection? And I talked about how there are two different types of model building exercises. There's explanatory modeling and there's predictive modeling. If the goal is explanatory modeling, then we want to be careful about overly referring to the data itself to build the model. Things like formal model selection or variable selection algorithms can cause problems. So let me demonstrate that. Okay, here we go. So beginning of line 160, I have a blurb on explanatory versus predictive modeling. There's a distinction between these types that like we talked about last time. An explanatory model is primarily interested in estimating a model coefficient and doing inference on it. What's the effect of treatment on the response, for example? With a predictive model, on the other hand, the interest is primarily in just accurate prediction. So we have two kind of distinct tasks. When we do formal model selection, like using p-values or aggressive algorithms to decide which variables go in the model, any transformations to do for the data, we could try 50 different transformations of our data and fit the model each time and pick the transformation that gives us the smallest p-value, for example. That's kind of like cheating. That's overfitting the data. So the way inference and explanatory modeling is designed to work is like this. You write down the scientific question beforehand, you obtain your data, and using that data, not fishing around in the data, but using that data and the variables that you decide on based on exploratory investigation, you do inference. And that should look like one p-value for every scientific question, one p-value or one confidence interval. Model selection has an additional step embedded in there. We obtain the data. We do inference of some sort to decide on the model. Maybe we compute p-values for a bunch of covariates in the regression model, and we remove those that have big p-values because they don't look like they're necessary, and we're looking for a, quote, parsimonious model. The problem is that if you do that, and you wind up at the end of that routine with a single final, quote, best model, the p-value that you put on the coefficient for, say, the treatment effect does not represent, it does not accommodate or incorporate all the stuff that you've already done with the data. So what that can mean is the p-value does not mean what you think it means. A p-value of 0.04 after doing model selection could actually correspond to a higher type 1 error rate than the 5% that you compare it to. A 95% confidence interval that you try to compute for that beta coefficient in that final model may not have 95% coverage. The issue is we are overusing the data, essentially. We are using the data both to choose the model and then fit the model. And the inference part, p-values and confidence intervals, they need to know about everything we've done with the data. One simple example, if we wanted to test a single mean, forget about regression, suppose we wanted to test whether a single mean equals a particular value versus an alternative hypothesis. We'll say it's not equal to mu 0. And suppose we observe a sample of size 15 or something, a small sample size. Then in order to test this or do a confidence interval, we would do a t-test or a t-based confidence interval. The t statistic would look like sample mean minus the mean under the null divided by our estimate of the standard deviation of the sample mean. And when we do a t-test with a small sample size, we assume normality. That's one of the penalties of using a t-test with a small sample size. Your data need to have come from a normal population. Under normality, x bar, so when normality holds, when the data come from a normal population, x bar is itself normal with the right mean and population variance divided by sample size. So if x bar is normal, why can't I compare this statistic to a normal distribution, like standard normal? The t-test doesn't do that. It replaces that normality, even though x bar is normal. This is not true. And the reason it's not true is because we have already used the data to estimate two things. The main one that hurts here is that we had to estimate the variance. If I knew the variance and I could just plug in sigma in place of s, then I'd have a normal distribution. But using the data to estimate something that goes in the denominator, that something in the denominator is a random variable because it's a statistic. It has a random distribution. And mathematically, the ratio of these two things is not normal. It's t. So I present that as kind of a kind of similar to this issue. If we did not account for, if we did not own up to doing this estimation in the denominator, then we would look at that normal distribution, but our inference would be not quite right then. The t distribution is there because that's what happens after you use the data already to estimate something first. So, not the best example probably, but maybe it gives a little bit of intuition. So what I'm going to do here is a simulation. Let's consider a continuous response variable and 5 continuous covariates. So we have an Excel spreadsheet with a column containing the response variable, and then we have 5 other columns containing covariates that are continuous. Suppose that the true model is that model, which would mean none of those covariates in our data set are related to the response. So they're all essentially meaningless covariates. They are not explanatory. But we don't know that. We just have a spreadsheet with covariates in it. And a couple of possibilities would be, one, I think those 5 covariates, as far as I know, I won't know what the true model is in practice. But as far as I know, we measured these 5 covariates for a reason. So I'm going to consider them as in the model. I'm going to put them in the model. If I think they are, if I think they are reasonable to use as predictors, if I believe that there is a good possibility that they are related to the response, then I'm going to put them in the model. even if they don't have a small p-value at the end of fitting this thing. Another alternative would be to use some formal model selection algorithm, like stepwise model selection. So we could say, I have these 5 covariates, but I don't know what the best model is, so let's throw an algorithm at this and consider a variety of choices and pick the one that, quote, fits best. So what I'm going to do is simulate 500 times. Each time we're going to simulate from the true model. The covariates are not in here, so the true model does not have them. But we believe that those covariates could be relevant, and we want a model to do our explanatory inference. So we're going to choose our model before looking at any p-values. I'm going to put all 5 in there. The other thing I'm going to try is a stepwise algorithm. So I've got both types of models happening in here. Okay, so if what we're going to do at the end of this is test whether the 5 covariates with an f-test, we're going to test whether there is any effect of those 5 covariates. These 5 covariates could be like dosages of 5 different drugs. We are considering a cocktail of 5 drugs to treat some health-related response. And we're interested in, do these drugs have any effect? One way to ask that would be to ask whether all 5 of those variables belong in the model or not, like an f-test. So we could consider model that looks like this: x1i, beta 2, x2i, dot, 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 beta 5, x5i plus epsilon I. And if each of these represent, like we're saying, some dosage of 5 different drugs, then our scientific question of is there an effect of these drugs considered together would correspond to the null hypothesis that beta 1 and beta 2 dot, 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 and beta 5 equal 0 versus an alternative that is not that. We can test that hypothesis using either a likelihood ratio or f-test. I'm going to use an f-test. If, on the other hand, we did model selection using like stepwise variable selection, then we might end up with a different model. Maybe the model selection algorithm gives us beta 1 x3i and beta 2 x5i. So it's selected only a subset of the variables to use as covariates. Now my question, my test that I want to do, is there any treatment effect, would be a different null hypothesis. Here it would be, is beta 1 and beta 2 equal to 0? In the simulation, we're going to do both things. We're going to say, based on domain expertise, prior beliefs, and that type of thing, I'm going to include all 5 covariates. And then my one test, my one p-value, is going to be based on a likelihood ratio or an f-test. Compared to model selection algorithm, and then do inference on the selected model. Okay. So I'm going to keep track of the decision that we make. Plain style, and by plain I just mean you set up one model at the beginning of things, you fit that one model, you compute one p-value for that model. As compared to the decision that we would come to after doing model selection. So we're going to let the stepwise regression run and pick the, quote, best model, and then we're going to use that model to test, is there a treatment effect? So if we're doing valid inference, then we should, in this case, because the true model is the null one, we said at the beginning of the script that in truth, these are not part of the model. They have nothing to do with the mean of the response. So this null hypothesis is true. Every time we do a simulation in this simulation script, this null hypothesis is true. What that means is, however I do inference, explanatory inference, I should only reject this null hypothesis 5% of the time if I compare it to a p-value of 0.05. If it's valid inference, if this routine is valid, then what I should see in the simulations is I only commit a type 1 error 5% of the time. So we're going to record what our decision is in each simulation for the best fitting model and for the one that we wrote down at the very beginning. And then we'll compare what proportion of the time did we get a p-value less than 0.05. So I'm just going to run this and show you the punchline. So writing down the model beforehand and doing one test Okay, so for those following along online, we lost 3 minutes of audio. Let's see how to summarize. Big picture is you want, if the goal is inference or explanatory inference, you want to pick your model based on domain expertise, prior results, exploratory pictures and things like that, not some formal algorithm that uses the data aggressively to pick the model for you. It's different from predictive modeling. Predictive modeling, it's more appropriate to try lots of different models. The reason it's okay there is because we're using something like cross-validation or holdout test set to give us an honest assessment of what the final model is able to do. So it's still an issue even in predictive modeling, but we guard against it by the way we assess accuracy. Mm-hmm.
So my feeling from this simulation is if your true model is the 5 drugs, they don't have an effect. So the type 1 error, the increase of type 1 error comes from when you do the model selection, you kind of pick data to force them into to fit the model, right?
Yep.
And in the process, you are introducing like a bias into this coefficient, and that's why you are getting a higher type 1 error rate. So, but if in real life you don't have a real like any good models in the beginning, so I was thinking if you take half of the data to do model selection, and then you take the other half to test this null hypothesis, is it going to increase the type 1 error?
Okay, so question was, what if you have this explanatory goal and you take your data set and you take half of it to do model selection, to pick the best model somehow, and then you use the remaining data to compute p-values. I think you're going to have the same issue because the data in the first half is representative of the second half. There's nothing systematically different. So I think it won't be as bad. I think it will not be as bad. This simulation is causing us to call significance due to just random stuff. So randomly, there may have been that if you include these two variables, you get something moderately significant. So if you do separate it, I think you would guard against that somewhat, but still have, I think, the same potential problem of using, I'd have to look into that. I think the best advice is to make your decisions on your model based on prior research, what have people seen to be relevant to explaining this problem, and exploratory pictures as much as possible. Not p-values, not automated algorithms, but I'm going to make a scatter plot of my response variable versus x1. Does it look like there's anything there? If not, I won't use that variable. So generally speaking, I think people try to include variables if there's exploratory evidence to suggest them, and or if there's just domain reason to believe that they make sense. Like gender, for example, makes sense to include in pretty much any model, or race in a medical setting. So even if gender's coefficient is not small, if the p-value for that gender coefficient is not small, in a clinical trial setting, you would tend to keep it in there because it's important for the explanatory process. If you're going to explain survival from cancer, gender is a sensible variable to have in there. So there is an art form, I think, to building models and deciding on models. And I think some of it comes from experience. My best recommendation is try to guard as much as possible from letting the data decide what the model is. Okay, I have a handful of things in here that you might find interesting. One thing that I show is sample size calculations. So if you've ever had to design your own study, I'm going to do an experiment on mice, and we're going to compare the body mass index of mice under 2 diet programs. What a question you have to answer is, how many mice are you going to buy? And resources are always limited, so you want as many mice as you need, but you don't want to buy more mice than you need. If you can detect a clinically relevant effect using 30 mice, then there's no sense wasting money in getting 100 mice. If you can get a small p-value with 30, you don't want to spend to buy 100. Sample size calculation is an effort to decide just how many do I need in order to detect a specific effect size. So the usual routine is you think about an effect size that is relevant. That might be, nobody cares if you can give somebody a pill and decrease their BMI by 0.001%, arguably. But we do care maybe if where's the smallest effect that we care about? You talk to a doctor or a dietitian to answer that kind of question. Maybe it's 20%. 20% is the smallest effect size that we would consider interesting. So let's consider how many mice would I need in order to have a sufficient amount of statistical power to detect an effect of that size. The sample size calculation game requires that you specify the effect size you want to be able to detect, the type 1 error rate you're comfortable having, and the amount of power that you want at that effect size. You decide on all those things, and then in some cases, there's an analytical formula that says, if you're doing a t-test, for example, the sample size required is plug and chug. But there are other scenarios where there's not an analytical expression, and you don't know a formula to compute the sample size. Suppose you're doing logistic regression, and you have 5 categorical predictors and 3 numerical predictors, as well as potential interactions. I don't know a formula for what the sample size to detect a 20% effect size on beta 4. So what I will just briefly comment on here and show you one little illustration is, if you don't know the formula for the answer to some statistical task, it may be that you can use a simulation to approximate it. For example, suppose we're going to do a 2-sample t-test with equal variances. And suppose we have an estimate of the variability. Prior studies have shown in this context that the variance of this response variable is somewhere between 3 and 5. So maybe to be conservative, we'll pick the higher value of that range, 5. I'm going to say the variance is 5. Suppose I want 80% power. So people choose a variety of common choices of power, 80%, 90%, 95%. 80% is common. What I'm going to do in the simulation is consider a variety of effect sizes, ranging from none up to very substantial. And for each one of those effect sizes, let's consider a variety of sample sizes that we might go pay for. If I do a simulation, say 1,000 times, I can simulate under this scenario. Let's assume the variance is 5. Let's assume the mean difference is whatever the effect size we're going to have at each iteration. And let's consider a variety of sample sizes. For each one of those scenarios, each choice of one of those things corresponds to a single scenario that we can simulate from. We can do a simulation and approximate the power. What would be the power under this scenario with a sample size of 10 based on a simulation, 1,000 simulations. So let me just show you what you can do with a simulation. There's more code here than we need to look at, but I want to show a picture. That's going to take forever. I have a faster version. Let me pick more carefully which code I run. R does not like nested loops, and it can get really, really slow if you have a loop over this many things, and inside of it you have another loop over that many things. So this code is ugly, but it is more efficient because it's using vector operations to do calculations more efficiently. Okay. So here are power curves. If you want to know sample size required to achieve a particular power to detect a particular effect size, you could consider a power curve as a function of the sample size. So I have for 4 different effect sizes, one is that the mean difference in these two groups is equal to 1. And then it increases to 2, and then 3, and then 4. So the black curve is simulation-based power curve as a function of sample size. For example, if n is equal to 40, we go get 40 mice, we only have power about 0.1 to detect this effect size. As you increase the effect size, it becomes easier and easier to detect it. So the red curve is shifted above the black one, the green one shifted above the red one, blue one shifted above the green one. So you might make a picture like this for your PI collaborator and say, okay, here's your options. What effect size do we feel like we need to get? You tell me the effect size, I'll tell you the sample size that you need. Let me see what else I've got in here. Another bit of trivia, maybe you might call it, about doing inference is we saw in this picture that the bigger the sample size, the bigger the effect size, the bigger the power generally. It's easier to detect a difference when the difference is big. But if you increase the sample size to big enough, you will always find a small p-value. That's relevant in the real world. So for example, not that many years ago, there was a big observational study, longitudinal study of nurses. And for the nurses, they observed like cardiovascular health and cancer incidence, cholesterol, a bunch of different things. And they also kept track of risk factors and demographic status and medications that they were on. And part of the implication of what they saw as they were observing these data, this was not an observational study actually, it was a clinical trial. This was a clinical trial of women, and the treatment agent was hormone replacement therapy. So these were postmenopausal women, and they were given either hormone replacement therapy or something else, some control. And this was a huge study, like thousands of women. And after some period of time, often what they do in clinical trials is they plan to have the trial going for 5 years, but they are also taking a peek at the data at interim points. The reason they do that is to monitor, are there adverse effects that are substantial? Is this drug more dangerous than we thought it was? And potentially stop the trials early. They could also start the trials early if it becomes clear enough that there's going to be a statistically significant effect. There's no need to continue this study. This drug works, obviously. So in this particular one that I'm trying to remember, what they saw when they investigated the data before the end of the trial was a statistically significant difference in, I think it was breast cancer incidence between hormone replacement therapy and not hormone replacement therapy. And so it made headlines. You can imagine the head, CNN.com, new study suggests hormone replacement therapy increases your incidence of breast cancer, your risk of breast cancer, statistically significantly. P-value is small. And so there was some, repercussion of that. Many women went off of hormone replacement therapy. Many doctors recommended that you went off of hormone replacement therapy. But it was an illustration of this issue that even with a really small effect, if you have a big enough sample size, you'll still find a small p-value. So there's arguably a distinction between statistical significance and practical significance. This was a case where, yes, there was statistically significant difference in breast cancer risk, but arguably not practically significant. It was something like your chances of breast cancer are 1 in 10,000. If you take the drug, it's 1.5 in 10,000. And if your sample size is big enough, you can get a small p-value for such a small effect. So I just have a little simulation to illustrate that. Let's say we're going to compare two means. The mean in one group is 0. The mean in the other group is just barely different, 0.05. And then I'm going to consider a variety of sample sizes, from 10 all the way up to 10,000. And what you will see is that as you increase sample size, power increases. So what am I plotting here? These are p-values for simulated data for different sample sizes. And then the blue curve is a smoother to guide the eye. The actual difference is minuscule, 0.05. And yet, as you increase the sample size, if you have a big enough sample, that p-value is working its way down and down and down. So with a big observational study with tens or hundreds of thousands of people, you might find p-values that are small, but that don't really make practical, it's not something you would change your life over. So just something to keep in the back of your mind. Statistical significance, not the same thing necessarily as practical significance. And with a big enough sample size, you'll call anything significant. Okay, so one last simulation, and this is to motivate where we're going next week. Often in biostatistical applications, we have a response variable that is something like survival time, time till death. We have patients who have been diagnosed with AIDS, and we're going to randomize them to 2 treatment protocols, and we're interested in is there a treatment effect? Can we increase survival time among this population? So each person comes into our study, and we would most likely observe them over time. Come in at baseline, we'll randomize you to treatment or control, and then come back into the hospital once every 6 months for a checkup and just to check for adverse events and things like that. So person 1 starts out the study, comes in 6 months, everything's okay. Comes in 6 months, comes in 6 months, and then the next time, they died. So we know that they died after 2 years, 1 month, 10 days. We know their survival time. Another person starts the study, randomized to one of the groups, shows up in 6 months, everything's okay. Shows up in 6 months, everything's okay, and then disappears. Doesn't come back. There's no death certificate, but they just drop out. I don't want to do this study anymore. Or I moved to Beijing or something, and so I can't drive to Houston anymore. So what happens? What happens in that scenario? We have some people, for survival time, we see exactly how long they lived. We have other people, we see that they lived a certain period of time, but then we don't know what happened. They could have kept on going. They could have died right there, and we just don't know it. So, survival data. And a practical issue with survival data is this one. This is called censoring. This individual, that second individual, was observed to live a certain amount of time, but we do not know the exact time of death. So their time of death, their survival time, is said to be censored. Right censored specifically, as in the true number is some number bigger than that one, bigger than or equal to that one. It's also possible to have left censoring in different scenarios, like, well, we don't need to worry about it. There's there's left censoring, right censoring, there's also interval censoring. So survival analysis is all about what do we do with data like this. One option would be all the people in my study who were censored, I'm just going to remove them. The problem with that is in a particular survival study, you might have 20 or 30% who are censored. And then you just lost a huge chunk of your data. So all that power that you were ready to have to detect a particular effect size, you don't have that anymore because you lost a big chunk of your data. So you don't want to just throw them out. Another option would be, let's go ahead and just say they died then. That's the last time I know for them, so we'll just say they died. The problem with that is that you're going to get a biased estimate because the truth is somewhere bigger than or equal to that red one. So if we replace every censored individual with the time of their censoring, we have biased inference. So that's not an option. Okay. So I'm going to show you beginning next week what we can do. We can do regression, is the good news. We can fit regression models, just like we can with correlated data, we can fit regression models to censored data. But just to illustrate the issue, here's a little simulation. So univariate sample with right censoring. And let's consider what happens to our inference if we do that kind of hack solution of replacing the censored time with the actual death time. So you moved to Beijing after 2 years, 1 month. I'm going to say you died in 2 years, 1 month. I've been to Beijing, so I know the air quality may be about the same. Okay, so here we go. A sample size of 100. We'll do 1,000 simulations. And step 1 is to generate some numbers. So I'm just going to do normally distributed, we'll call them survival times. And then to create censoring, I'm going to randomly pick 40% of the individuals. And for each of those individuals, I'm going to take their true survival time and subtract off something, some random number. Because I don't know the truth, I know some number less than or equal to the truth. So for 40% of my data, I'm going to pull it back just a little bit, randomly generated some little bit to be the censored time. Then, what happens if we just proceed as if every single number is a survival time? So I'll compute y bar, I'll compute s, and then we'll do the usual t-based confidence interval, or z-based in this case. And we'll keep track, yes or no, did the confidence interval contain the truth? The true mean in this simulation is 0. That's the number I picked. So if the confidence interval is working, if inference is doing what I claim it to be, then 95% of my 95% confidence intervals should contain the truth. I should have 95% covered. And you can guess we're not going to achieve that because treating the censored time as the actual survival time is going to systematically underestimate survival time, bias in the survival time estimates. I computed what I claimed to be 95% confidence intervals, but they were really 83% confidence intervals. All right, so Monday we'll start doing survival data. We'll look at something called the Kaplan-Meier survival curve estimate. And then Wednesday or Friday, we'll see regression techniques. So there's a model called Cox proportional hazards regression model, which is widely used with survival data. We'll see what it is, how to use it, how to diagnose it, and we'll play with a bunch of different data sets. Okay? Have a good weekend. Uh-huh.
Are you going to change the deadline of homework or still?
Do we need to? You need more time?
Can you show us an example of the spaghetti plots? I didn't find it.
Okay. Let's see. How about I post some example code to the discussion board? Question was for example spaghetti plot. I'll post an example to the discussion board. And just let me know if we feel like we need more time on the homework. I'm flexible. I can do that and push it to Wednesday or something. I'll be listening.